Swayam Prabha. Digital India. Educated India.
Okay, so let's continue with kinetic theory. So just quick recap. So we are basically assuming that matter is made up of many molecules, and molecules have no size, like they are point-like particles, they are dimensionless, they only collide with the walls of the container, and we derived quantities like pressure and temperature, right? And basically what we have been doing subsequently is we are relaxing all those assumptions one by one that we made in the very earlier in the very first or second class, right? So in a class before, like 2 classes before, we basically relaxed the assumption that the molecules are point-like or dimensionless molecules, and when we assume that they have some finite size, so we considered the situation where they can undergo collisions, and because of that we defined the concept of mean free path, which is like the average distance these molecules travel between two successive collisions, right? And in the last class we went one step ahead, and we basically assumed that what if we can systematically drive that collection of molecules out of equilibrium, right? So basically, so a quick recap from the last class. So we basically derived, so we drive system out of equilibrium, right? And we systematically did that in 3 steps, right? In 3 ways. So one was by introducing a velocity gradient, right? Introduce a velocity gradient. Basically what we did was we basically created a situation where molecules along certain axes, they had a gradient in their velocity direction, right? The magnitude of the speed, essentially the magnitude of the velocity, and we saw that in such a situation there will be a net transfer of momentum, right, towards the gradient axis, and from that we defined a transport property which we called coefficient of viscosity, right? Viscosity, and we saw that this viscosity, which we denoted by the symbol eta, scales with temperature raised to the power half, right? And this more or less matches with experimental observations as well, right? And the second way we drove system out of equilibrium was through by introducing a temperature gradient, right? Which means along certain axes the temperature of molecules is greater, as so there is a temperature gradient along one axis. As a result, since the temperature is basically measure of kinetic energy, there is transfer of energy, right? And transfer of energy is basically heat, right? And in that case we defined the transport property as thermal conductivity, which we defined as K, symbol K, and this also we saw scales as temperature raised to the power half, and it is independent of pressure, same with viscosity. And the third way we did was the concentration gradient, right? And in the concentration gradient we assumed that there are more number of gas particles in one location in the space than than rest of the volume, and therefore there will be net transport of matter, right? And that transport can be measured by what's known as coefficient of diffusion, right? So we call it diffusion, or the term, the transport property was diffusivity, right? And we denoted this by the symbol D, and we saw that this scales with temperature raised to the power 3 by 2 divided by pressure and inverse of pressure, right? And this within reasonable window of these parameters, temperature and pressure, this holds really well, right? So this in some sense is success of kinetic theory in predicting the dependence of these transport properties on these parameters like temperature and pressure and so on, right? So this is where we ended the last class, but essentially throughout so far we always considered that the particles are non-interacting, right? So indeed we basically relaxed that assumption little bit when we assumed that the molecules can collide with each other, right? Which means they have a complete like repulsive interaction, right? But what leads to interesting phases of matter is not really repulsive interaction, it's the attractive interaction. And as you have seen, up to this point we haven't really considered that possibility, right? So we know that gases, if we reduce the temperature, they eventually liquefy and they even solidify, right? And like we saw that can only happen if there are finite attractive interaction or attractive forces between these two between the constituent molecules, and we haven't really considered that possibility. And essentially that is what we will do now. So we will basically make small corrections to this kinetic theory of gases by considering finite attractive interaction between these gas molecules, and we'll see how far we go with that, right? So basically what we'll do in today's class is we will go from what we defined as ideal gas to a real gas, right? So transition from ideal gas to a real gas, right? And the way, like if you remember, the way we defined ideal gas was no intermolecular interaction, essentially attraction, right? That is more important, attraction. But on the other hand, a real gas, as we know, since it liquefies, there is finite attractive forces between these molecules, right? So with finite attractive interaction between molecules, right? So that's what we will do today. Molecules. Okay. So let's proceed. So basically we will again, okay, so what we are going to do is what's known as real gases, right? Real as in what happens in reality, right? Again we are going to make few assumptions here, all right? While we make this while we okay, so basically what we will do is we will see the two important assumptions that we started with in kinetic theory, which are not really true in real gases, right? So basically so two assumptions which are not true, or basically so two assumptions that we made for ideal gases that are invalid for a real gas, right? And the assumption number one is that gas molecules are dimensionless, right? So which, if you think about it, this basically limits us to the parameter regime where the density of gas is very low, right? Now you can imagine if I keep stuffing more and more molecules in a container, the density will start increasing if the molecules have finite dimensions, right? If they are not, then the density doesn't even make sense. But if they have finite dimension, the packing density will keep on increasing, right? So that is something that will break down. And the other assumption that we made for ideal gases is that molecules only have kinetic energy and never undergo attraction, right? So what I am saying is basically both these assumptions are not true for a real gas, right? And we have to make corrections for these, all right? And if you actually think about it, all the, I mean these assumptions they break down essentially in the regime where you have either have low temperature or you have high density or pressure, right? So if your gas is at very low temperature, its kinetic energy will be very low, and if there is any attractive interaction between those molecules, they will keep becoming more and more important, right? So we can assume, or we can imagine that a real gas, it will become more and more important for us to consider the gas as real at low temperatures, and same goes with gas at very high density, right? So when the density of, so remember, like when we say that gas molecules are dimensionless in ideal case, so what we basically assume is that the size of gas molecules is much smaller than typical intermolecular spacing, right? But now if the density of this gas is very high, the typical intermolecular spacing, and when we say it's very small compared to what, right? So we say that the intermolecular spacing is much smaller than typical dimension of the gas molecule, right? But at very high densities, when the gas molecules are much closer to each other, um, the inter and at the moment when intermolecular spacing becomes comparable to the diameter of the gas molecule, that assumption breaks down, right? So therefore we imagine that at very high density, or similar goes with very high pressures, the first assumption doesn't hold true, right? So so basically what I'm saying is uh, uh, so um, so so basically okay, maybe I can write down this again, so in a proper way. Okay, so what I'm saying is uh, a gas would behave uh, so basically um, uh, assumptions break down, so break down at either at low temperatures, low T, or high density or pressure, right? So this is where we imagine that it is more and more important for us to start worrying about these assumptions that we made for ideal gases. Okay, so at this point you might be wondering, right, how do these gas molecules even undergo attraction, right? So we know that the molecules in this gas, they have equal number of protons and electrons, right? So they are basically neutral particles, and neutral particles, they do not undergo any electrostatic interaction, right? So how is that even possible? Okay, So maybe I'll quickly give you a physical insight of how that thing happens. All right. So basically, how do neutral molecules attract each other, right? Right. So that's what we have been saying repeatedly. Okay. So let us try to visualize, right? So say we have a molecule, and let's say it's just an atom, right? So single atom like hydrogen or something, right? So it has a positive charge in the center, which can be its nucleus, and there is an electron cloud surrounding this nucleus, and there is, say, in its very close to it, there is another molecule which again has a positive charge and a negative charge. And when these molecules are very far from each other, the center point of this distribution of positive and negative charge, that overlaps, right? So therefore this molecule these molecules are basically symmetric in terms of the charge distribution. But when they become very close to each other, right, especially that happens at very high densities, so these charges can start interacting with each other, right? And typically what happens is, so this charge distribution can start getting distorted, right? So essentially, so this negative charge can start interacting with this positive charge, and as a result, the distribution of these charges that attains a typical dipole, right? So the center point of these charge distributions that can displace, and there can be a temporary dipole formation with these charges, right? So basically this positive charge and negative charge, they can separate from each other, similarly with other molecules. And typically these otherwise neutral molecules, they can undergo what's known as they become charged dipole, and they can start attracting each other, right? And typically this so if I define a distance r between two molecules, okay, so typical dipole attraction or attractive potential, okay, that scales with r raised to the power 6 with negative sign. All right. So that is like the attractive forces that can emerge when two molecules, they become these charge dipoles, and that is basically because this plus charge can attract the negative charge of these electron clouds, and that leads to net attractive interaction. But you can imagine that if we bring these atoms or molecules much closer to each other, these electron clouds, they will continue to repel each other, right? So this is at large r, this is what we assume. So when molecules are far away from each other, they will have some net attractive forces between each other, which scales by 1 by r raised to the power 6 typically. But at low r, so the electron clouds can repel each other, and that will typically lead to an repulsive interaction, right? And I'll not go into details, but that repulsive interaction or that repulsive interaction potential, that scales with inverse r raised to the power 12, right? So therefore the net potential between these two molecules, that takes this typical form. So I can now plot, so maybe I can write, so the total interaction potential goes something like minus 1 by r raised to the power 6 r raised to the power 6 plus 1 by r raised to the power 12, right? And this is a function, okay. So I can plot this v of r. So maybe I can first draw this attractive term, right? So this basically goes like this, right? And the repulsive force, which is with red color, that diverges, right? And the total interaction potential in green will look something like this. So that takes a form. So if you sum these two functions, so this is how a typical interaction potential between these two molecules look like, right? So basically this is minus 1, this is 1 by r raised to the power 12. This one is minus 1 by r raised to the power 6. This is the attraction, and this is the total potential, right? So this is the total potential V of r, all right? And you can see that within certain range, up to certain distance, say r0, okay, so what will be the forces acting between these two molecules? So force or force would go as minus dV by dr, right? And you can see that and this is attractive, right? So wherever the slope of this line is positive, you will have attractive force, right? So therefore, between the distance is greater than r0, for r greater than r0, there is net attraction. Okay. So because of this this dipole formation, these molecules can undergo net attractive forces. Okay. So this is basically the origin of this attractive interaction between molecules, which we had been ignoring so far, right? And now that we will start considering this for a real gas. Okay. So now we can ask how does this fact so what actually happens in experiments, right? So how do attractive or how does attractive interaction change experimental observations? Okay, so this is what we will see, and this was actually so this was actually seen in what's known as Andrews experiment. And what he did was, he basically took a volume of carbon dioxide, and he started applying. So he started lowering the temperature of this gas, right? And this is what he observed. Okay. Okay. So typically, okay. So this was done on carbon dioxide. All right. So we know that for an ideal gas, the pressure scales with inverse volume at constant temperature, right? This is called Boyle's law, all right? And when he performed this experiment on carbon dioxide, so this axis is pressure, this axis is volume, all right? So when he performed this experiment at 48 degrees Celsius, okay, and this pressure is in I think in units of atmosphere. Okay, so this pressure is in atmosphere, and this volume is in cubic centimeter cube. All right. So when he performed this experiment at 48 degrees Celsius, he saw that the pressure basically decays inversely with volume, as we expect from Boyle's law. All right. But as he kept on increasing the temperature, decreasing the temperature. Okay, maybe I can write. So at 48 degree, okay, So the pressure scaling inversely with volume remained valid. Okay, so that remained valid, or which you can basically see that d by dv of the quantity PV was 0 for all P and V values, right, at 48 degrees Celsius. But when he reduced the temperature to the value 32.5 degrees Celsius, okay, so he observed deviation from P scaling with inverse V, okay, which basically implied that the derivative of this quantity P times V was non-zero, all right, over some range of these P and V values. And how does that look like? So there was deviation from this behavior. We can so okay, so there was deviation, all right, and so much so, so let me so much so that at certain temperature 31 degrees Celsius, okay, there was a point where this curve basically became flat, okay, so let me so there was a point, let's call this point X. So this is at 32.5 degrees Celsius, this is at 31 degrees Celsius, okay. So at point X, so this d by dv of PV basically became flat, and it took a constant value of P0, right. So this is P0, and this was about 72.8 atmosphere, right. And when he lowered the temperature even further, okay, so say at something like 21.5 degrees Celsius, so what he saw that this isotherm basically became flat. Maybe I can draw it little lower. So this isotherm basically became flat, and then it decayed, okay, and this is at say 21.5 degrees Celsius, right. So at 21.5 degrees Celsius, he saw that above certain volume, so at high V, the P scaled inversely with V as expected, right. Let's call these points, this point B, and let's say this is A. So basically between B to A, okay. So but between, let's call this point C. So but P was constant between point B to C, all right. But we can call this A, but the but again, but below, but P increased drastically, abruptly between A to C, right. So these were the experimental observations, right, and you can already see that this is a complete deviation from what we expect from Boyle's law, right. From Boyle's law, we expect these isotherms always to follow the mathematical form, which is P going as inverse of V, all right. And like I said, there was this special point X, okay, which was defined as some parameters Tc, Vc, and Pc, right. At this point, there is certain temperature which is 31 degrees, there is certain pressure which is, let me call this maybe let me call this PC to be consistent. So this is PC, and similarly this point is BC, right? And this is called critical point. Okay, and so these were the isotherms that he observed, and also he made these observations that that above this point X, the gas, the collection of these molecules, carbon dioxide, was always in a gaseous phase, right? But below this X, there was condensation. Okay, so the gas started liquefying, and there was a phase coexistence between the gas and the liquid phase, and below this point C, the gas always existed in liquid phase. Okay, so gas was in a pure liquid phase. So therefore he realized that since this gas is undergoing some liquefaction, right, it is getting liquefied, there must be some attractive interactions, right? And there was this deviation that started appearing much before the critical point was achieved, right? So critical point basically is a point where we see the transition from gaseous to liquid phase. Okay, so basically the conclusions that he made, or the conclusion of this experiment is that okay, so the main conclusion here is that since gases liquefy, there must be an attractive interaction between molecules. Right, so there must be attractive interaction between molecules, and also so the ideal gas behavior breaks down close to the critical point, right? So basically we need a better model or better theory to understand or to explain these observations. All right, so maybe very quickly I can quickly mention. So when we did these experiments for various gases, so maybe okay, I can draw a table for various. So when these experiments were repeated on various gases like helium, hydrogen, oxygen, carbon dioxide, so these were the critical parameters that were observed. So this is in degrees Celsius, this is critical temperature, this is critical pressure, this is critical volume. Okay, so for helium this was minus 268, the pressure was 2.25, and the volume was 15.4. Similarly, minus 240, 12.8, 32.2, minus 119, 49.7, 2.32, 31, 72.8, and 2.17. Okay, but interesting fact is that the quantity RTC by PCVC. So remember, what is this quantity for an ideal gas, right? So ideal gas equation is PV equals RT. So it should ideally be 1. But they observed that for all these gases, this quantity was always close to 3. All right, 3 point something and 3.48. Okay, so this quantity didn't really change by much when this experiment was performed for different gases. Okay, so there is some mystery going on, right? So what is causing this number to appear? Okay, so basically what in the coming few minutes we will try to make corrections to the ideal gas equation, and we'll derive what's known as the real gas equation. Okay, okay, so let's jump to what's known as real gas equation. Okay, and it's also known as van der Waals equation of state. All right. Okay. So again, we'll work this out under again few set of assumptions, right? So some assumptions that go with this are, so the molecules interact only with their nearest neighbors. Right. So if you look at this this potential that we drew before, so you can see that the molecules will interact or attract each other over distance, any distance which is greater than r0. But we are assuming that the attractive force becomes negligible if those molecules are very far away from each other. And for simplicity, we will only assume attractive interaction between molecules which are closest to each other, right? So what's known as nearest neighbor molecules. And the other assumption that we will make is that the pressure is still well defined. Right, and what that means is, let me write that. So number of collisions with Waals per unit time does not change, right? Is same as ideal gas, right? So we are assuming that even though we are very close to the critical point, these gas molecules continue to impart momentum to the walls of the container and continue to impart some pressure which is well defined. All right. So in some sense, you can see that we are still assuming the gas remains in what's like gaseous phase, right? It never really liquefies. All right. So these two assumptions we make. So now under these assumptions, we'll basically start making corrections to the ideal gas equation, right? So let us go step by step. Let's do, so, okay. So this first thing that we'll do is correction to the ideal gas equation for finite molecular size. Okay. So what do we mean by that, right? So remember, in ideal gas, we assume that gas molecules, they are dimensionless, right? They have no size. So therefore, every molecule in a particular container volume V will experience the total volume V. But now, since we are saying that that is not true, the gas molecules do have finite dimensions. So they do occupy some volume in the space, right? So the volume felt by the other molecule is the volume of, say we have just two molecules in a container. The volume felt by the second molecule is total volume minus the volume of the first molecule. So basically, for an ideal gas, so all molecules all molecules have volume V, right? Because other molecules have zero volume. But with finite size, with finite size, the actual volume is not V, but it is V minus some correction term, right? So since other molecules have finite dimensions, so we have to subtract something out of that total volume. And what is that attraction term? That is what we have to now basically estimate, right? Okay, so let us do that. So let's imagine, like so let's say we have one molecule. Again, we are assuming molecules are spherical for simplicity. So say they have radius r. Okay. Now let's say there is another molecule which is also spherical, which has radius r. But since these molecules can't really overlap with each other, right? So the centers of these two molecules, they can never come closer to each other than a distance of 2r. All right. So basically this volume which I am coloring in red is basically an excluded volume, right? This is excluded volume, right? So this molecule cannot really occupy this space, right? So therefore it is losing this volume out of the total volume of the container, right? So and what is that volume? So this excluded volume is basically let's call it VE. This is 4 by 3 pi times 2r cubed, right? And you can see that this is 8 times 4 by 3 pi r cube, and this is nothing but 8 times Vm, where Vm is the volume of single molecule, one molecule. Okay. So this is what single molecule contributes to this excluded volume. All right. So basically, but what we are interested in what is the average volume per molecule, right? So let us do that systematically. So let us fill the container one by one, right? So one molecule at a time, right? So say I give you a container which has volume V, it has no molecule. So if I add one molecule in it, right? So the available volume for first molecule is basically V minus Vm, right? Because this molecule has its own volume, so that the volume for this molecule will be V minus its own volume, at which we can assume that it is almost equal to V, because volume of a molecule is much smaller than the container volume, right? So because Vm is much smaller than V. All right. Similarly, available volume for second molecule, that will be V minus VE, right, which is the excluded volume, right? That is what is contributed by one molecule, right? Similarly, we can go to the third molecule, that will be V minus 2VE, and so on, right? And so on, and we can see that for nth molecule, this term will be V minus n minus 1 times VE, right? So therefore, what will be the average volume per molecule, right? So average volume per molecule, so that will basically be, let's call it V average, which is 1 by n times sum of all these volumes, right? Sum of all these volumes. So V plus V minus VE plus V minus 2VE plus so on, plus V minus n minus 1 VE. This is what we have, right? And this can be written as 1 divided by n sigma I going from 1 to n of V minus I minus 1 VE, right? And since sigma I going from 1 to n I is n into n plus 1 by 2, and here and basically just using this equality, we can see that the average volume becomes 1 by n. So this first term will give you n times V minus n into n minus 1 by 2 times VE, right? And assuming n is very large, so we can safely assume that n minus 1 is almost equal to n, right? So remember, we are dealing with typically like 10 raised to the power 23 gas molecules, right? So therefore this average volume becomes 1 by n times nV minus n squared VE by 2, and if you simplify this just becomes V minus n VE by 2, right? where remember VE is 8 times Vm, right? 8 times the molecule of the volume of single molecule. All right, and if we put that here, we can see that this average volume is basically V minus N VE by 2. All right. So that's what I wrote here, and this becomes V minus 4 times N Vm, right? So let us assume, so say we started with 1 mole of gas, right? Say N equals Na, which is Avogadro's number, right? 6.023 into 10 raised to power 23, in which case we can write V equals V minus 4 times Na times Vm, right? And let us call this quantity as B. So let's just define this as B, where B is 4 Na Vm, right? So this is the correction term for 1 mole of gas, right? But say we have n mole of gas, right? So for n moles, your total number of gas molecules will be n times Na. So in which case your correction term will become V minus 4 times n 4 times n Na Vm. This is nothing but V minus Nv. Okay. So therefore, the correction to the ideal gas due to finite volume of these molecules goes as follows. So this basically looks like P times V minus Nb equals nRT, right? For 1 mole, this was P times V minus V equals RT, but for n moles, this is what the correction looks like. Okay, so this is how the ideal gas equation gets modified when we consider finite volume of gas molecules. All right, now let us do the second thing, right? Now let us do the correction for intermolecular attraction, right? Intermolecular attraction. Okay, so how do we do that? So remember we are dealing, so let us try to visualize this, right? So say you have these many gas molecules in this container, right? And like we saw, these gas molecules, since they can act as dipoles, so they undergo some attractive interaction, and we can see that a molecule which is sitting inside the container somewhere in the middle, it on average it experiences an attractive force equally from all directions, right? So therefore net force on this molecule, right, this molecule, so net force is 0, right, because it is being pulled from all directions equally. But if we look at a typical molecule which is sitting close to the edge, for example this one, this will feel more force towards the inside of the container because there are no molecules on the other side, right? So therefore this molecule will feel net attractive force towards or away from the wall, right? Away from the wall. And you can now imagine how will that change, right? So remember we were assuming these gas molecules, they are going and hitting the walls of these containers. But since for this typical gas molecule which is very close to the wall, there is a net attractive force which is keeping it away from the wall, right? So therefore the pressure of this gas will go down, right? Because it's not really hitting the wall with the same momentum. All right. So therefore, due to net attractive force, on molecules close to the wall, there is reduction in pressure. And we have to correct for this, right? We have to correct for this pressure term, right? So remember in earlier case when we were dealing with volume, right? So as an observer who is sitting outside, the volume that we assumed the gas molecules have is equal to the container volume, but that was actually, but the real volume was less than that, because we knew that there are gas molecules who are also occupying that molecule. So therefore we subtracted this correction term, right, because the real volume was less than that. But on the other hand, in this case, the measured pressure, right, is okay. So for volume case, the ideal volume was V, but we knew that the real volume is less than V, so therefore we subtracted a correction term. But in this case, we know that the measured pressure in the ideal gas is greater than what it is in reality, right? So therefore in this case, the correction term, okay, so let me write that, right? So measured pressure in the ideal case is smaller than the real pressure, right? Which basically means the real pressure is basically equal to the ideal pressure what would exist ideally plus some correction term which we have to estimate now, right? So therefore the correction term is added here, right? And this is what we have to find. All right, so basically our next goal is, what is this pressure, right? So since the pressure, the real pressure is less than what we observe, what we believe, right, because there is net attractive force acting on this molecule which is about to hit the wall, we have to add a correction term, right? And now what is that correction term? Let us try to estimate that, right? Okay, so how do we do that? So let's say we have, so let so say, so for n mole of gas, right, in volume V, right? Okay, so basically this is how it typically looks like. So we have this collection of gas molecules, right, and every molecule has certain nearest neighbors, right? So this molecule is only getting attracted by these its nearest neighbor, and the same applies to all the molecules, right? All the molecules. And we can imagine that this number of nearest neighbors will actually increase with the amount of gas per unit volume that we have, right? So if we have greater density of these gas molecules, there will be more number of nearest neighbors, right? So that is, so number of nearest neighbors, let me just call it that, nearest neighbors, that should be proportional to the density of gas, right? So n divided by V. And also okay, and since the attractive forces or attractive interactions are only coming from the nearest neighbors, so interaction strength, interaction energy should also be proportional to number of molecules multiplied by number of nearest neighbors, right? Because the interaction energy is a property of a pair, right? So one molecule interacts with another molecule, and if we have more pairs, we have more interaction energy. So therefore we have to multiply this, the number of molecules, by their nearest neighbors, right? And you can see that this is basically proportional to n times number of nearest neighbor, which scales with n by v, and this is equal to n squared by v, right. So this is the interaction energy, or rather A times this, where A is some proportionality constant. All right. So now, the next question is that how is this interaction energy related to pressure, right? Remember, we are making corrections to the pressure exerted by these gas molecules, right? So the next thing is, how is interaction energy related to pressure? Okay, so let us try to understand that. So remember, in ideal gas equation, we got the form that we saw was 1 by 3 rho v squared, right? So basically, this is the pressure exerted by gas molecule. This is the mass density of gas molecules, and this is the speed of gas molecules, right? So in some sense, the pressure is nothing but it's the energy density, right? So this is basically so 1 by 3 mv squared divided by v, right? Or in some terms, if mv squared is basically the kinetic energy per molecule, and we can see that the pressure is equal to the energy density, right? Okay, so since pressure of a gas is a measure of energy density, okay, so what we'll do is we'll say so what is the incremental change, okay, and if I change this volume, the pressure will change, right? So you can so if I reduce the volume of the gas, the pressure will increase, because there will be more and more number of greater the molecules of the gas will hit the container walls at higher frequency, so pressure will go up, right? So what is the incremental change in pressure corresponding to an incremental change in volume, right? So basically what that will be minus of d by dv. So let's say that incremental change in volume is dv times energy, right? And minus sign because the pressure will increase if I decrease volume, right? So to compensate for that, I put a minus sign in front, and now we'll substitute this energy value from here, right? So this is basically minus d by dv of a n squared by v, right? And this basically becomes plus a n squared by v squared. All right, and this is basically the change in pressure corresponding to an incremental change in volume dv, right? So therefore, what will be the real pressure, right? So real pressure from this equation, right? So that basically becomes P ideal, which was delta P. So we can just substitute this value here. So this is P ideal plus a n squared divided by v squared. Okay, so therefore the modified ideal gas equation looks something like this. So P plus a n squared by v squared times v equals nRT. Okay, so this is how the correction from the attractive interaction looks like, right? And remember here, what is A, right? This is an important parameter. A is a measure of attractive force between molecules. Okay. So in the ideal case, A was 0, so we get PV equals nRT, right? So therefore, now you can see that we have made two corrections to the ideal gas. The first, the correction term from volume looks like V minus NB, and the correction term to pressure looks like P plus AN squared by V squared. So therefore, the modified real gas equation, so the real gas equation becomes, so this looks like P plus AN squared by V squared times V minus NB equals NRT. Okay, so this is what the equation looks like. Okay, so this is the real gas equation. Okay, so let us see how it looks like, right? So say N is 1, right? So let's for simplicity assume that we have N 1 mole of gas. So therefore we can just write P plus A by V squared times V minus B equals RT, right? And from this equation we can write down the form of pressure, like the expression for pressure, which is as follows. Okay, so this is basically pressure as a function of volume. So basically where we are getting to is we are trying to understand Andrew's experiment, right? So after making all those corrections, can we try to explain this experimental result? Okay, so since in experiments he measured pressure as a function of volume at certain temperature, so and this is what we got in the real gas equation. Let's see how both of these these two compare with each other, right? So now you can see if I just plot from this way equation, if I plot pressure as a function of volume, okay, so if I plot pressure as a function of volume, so this is volume, this is pressure. Okay, so it's again it is a combination of two functions. So there is quantity B here. So the first term is inverse 1 by V minus B. So this is how it will look like. So let me do this with red. So this is V minus B, and the other term which I can do in blue. Okay, so that is so that is negative, and it falls as V squared. And remember, I have to stop at B because your volume cannot be less than B, right? So V minus B cannot really be negative; it can only go to 0. And if I plot the whole thing with green color, right? So the sum of these two functions will look something like this, right? So it will go down, but it will abruptly start increasing, and it will, so this is how it will look like roughly. Okay, and this is where it will diverge. Okay, and you can see that so at low A, the contribution of this blue line will be very small, and the pressure will decay inversely with volume, right, as we expect from Boyle's law. So P scales inversely with volume, Boyle's law, right? But at high A, right, when there are large attractive forces between these gas molecules, this term so at intermediate A, so the contribution from this term will start to creep in, and this curve will start deviating from inverse V form, right? And this is exactly what we saw in the Andrews experiment, right? at very high temperature, the P by so the PV was 0, right? So PV was constant at all these along the line, but then we started seeing this deviation, and this real gas equation also basically captures that trend, right? So P going as so P so deviation from P going scaling inversely as V minus P, right? But at high A, you can see that there is a minimum that we observe, right? Uh, Minimum, right? So we can discuss this in the next class, but what we have achieved after making all these corrections is that there is some so when we apply the real gas equation, right, and when we see the functional form of P as a function of V, this starts matching with the Andrews experiment, right? And in the next class we will try to basically continue from this point, and we'll see how we can make sense of this real gas equation and compare it with experiments, um, and that we'll do in the next class. Thank you.